Welcome to Talk Tensors, where we really get into the latest in machine learning research.
Great to be here.
So today we're doing a deep dive into a really interesting new academic paper. The title is, let me get this right, Unicorn, a universal and collaborative reinforcement learning approach towards generalizable network-wide traffic signal control.
Bit of a mouthful, but yeah.
It is. But for anyone, who's ever been stuck in traffic, this paper tackles something super relevant, using advanced AI to hopefully make traffic flow better in cities.
Absolutely. It's a huge problem.
Right. So this research looks at a new framework they're calling Unicorn. It uses multi-agent reinforcement learning, MARL, to try and optimize signals across a whole network.
Which is the tricky part, that network-wide aspect.
Exactly. The authors argue that, current adaptive systems are better than basic timers, but they still kind of struggle with the sheer variety, the complexity of real traffic.
The heterogeneity, as they call it. Mm-hmm. Different intersections, different traffic patterns.
Yeah, exactly that. So Unicorn's mission, basically, is to build a system that's efficient, sure, but also really adaptable to all these different traffic environments.
And it's crucial because congestion isn't just annoying, right? It costs time, money, fuel, affects air quality. It's a major issue.
Totally.
And while signal tech has improved, dealing with that diversity, different street layouts, crazy traffic fluctuations, how intersections influence each other, that's the core challenge.
So this paper is stepping in with a pretty novel approach using these ML techniques.
It really is a fresh take.
Okay, so let's get into this Unicorn framework then. How does it actually work? They start by tackling a pretty fundamental question, right? How do you get one AI model to control signals at intersections that might look totally different?
Yeah, that's the generalization problem.
And their solution is a unified way of looking at the traffic situation and the signal actions. Instead of whole roads, they break it down
into traffic movements.
Right, like a specific left turn or going straight from this lane. This becomes a sort of common language for the AI.
Regardless of the intersection-specific geometry.
Exactly. It doesn't matter how different they look.
And that's a key insight, I think. Older methods often look at intersections more in isolation or used, less detailed features.
Mm-hmm.
By focusing on these basic movements, Unicorn can get much finer-grained info about where the delays actually are and how changing a signal phase affects specific vehicle flows.
It's like going from a fuzzy picture to seeing individual movement.
Yeah, precisely. Much higher resolution in a way.
So building on that common language, they've got these two main AI modules. First up is the Universal Traffic Representation, UTR.
Okay.
Now, the UTR uses a specific neural network type. It's actually a decoder-only architecture, kind of like you see in language models.
So it's good with sequences.
Exactly. It takes the current state, queue length, moving cars, that stuff, and the current signal phase, and pulls out general patterns, features relevant across different intersections.
And the clever bit.
The clever part is handling the fact that intersections have different numbers of lanes, movements. It uses padding and masking techniques to manage that variability.
So it's like a universal translator for traffic data, trying to find the common ground despite the differences.
Yeah, that's a good way to put it. Like early machine translations struggling with different languages, early traffic systems struggled with different intersection designs.
Right, so the UTR tries to build that generalized understanding of flow, regardless of the specifics.
Allowing it to learn from lots of scenarios and apply it to new ones.
Makes sense. And the second module?
That's the intersection specifics representation, or ISR. This is where it learns the unique stuff about each intersection.
Okay, the local knowledge.
Exactly. They use a technique called a variational autoencoder, a VAE. Think of it like the AI creating a compressed digital fingerprint for each intersection.
A fingerprint. I like that.
Yeah. It looks at the traffic, the phase, even the physical layout info, lane lengths, speeds, and learns this compact code that captures its unique behavior.
And they do something clever to make these fingerprints better, right? Contrastive learning.
Yes. That's a really neat part. They train it to tell the difference. Okay, these two fingerprints are from the same intersection, just different times. But these two are from completely different intersections.
So it forces the model to make the fingerprints for the same place very similar, and fingerprints for different places very distinct.
Exactly right. It sharpens those representations, gives the AI almost an intuition for how traffic works at that specific spot.
That's pretty sophisticated. So you have the UTR for the general rules and the ISR for the local specifics.
Precisely. And then there's a final piece. It also looks at what the neighboring signals are doing.
The collaboration aspect.
Yeah. Using an attention mechanism, the AI figures out how one intersection's signals might affect its neighbors, leads to more coordinated decisions across the whole network.
So it's not just optimizing in isolation.
Right. And the whole thing is trained using proximal policy optimization, PPO. That's the reinforcement learning algorithm.
Learning by trial and error, basically. Adjusting signals to minimize queue lengths, maximize flow, getting that reward signal.
Yep. Minimize queues, reduce delay, that kind of thing.
And putting this in the context of, the broader ML research field, this paper really tackles a big challenge in multi-agent RL.
Which is?
Well, getting multiple AIs working together effectively when they're operating in different heterogeneous environments, that's been tough.
Okay.
Unicorn's approach, shared understanding via UTR, local context via ISR, plus the neighbor awareness, seems like a really interesting way to structure that collaboration.
So after laying all that out, they obviously had to test it.
Of course, the experimental section.
And it's pretty extensive. 8 different traffic data sets, simulations, real-world data. You mentioned Cologne, Monaco, also grid layouts, arterial roads.
Yeah, a good mix of homogeneous and heterogeneous networks. Some quite difficult. Places like Fengelen and Nanshan, too.
And they compared Unicorn against a whole bunch of other methods, traditional stuff like max pressure.
And other learning-based approaches. Some independent learning agents, some that share parameters, like Unicorn does things like MP-Lite, Attend-Lite, GESA, Hetero-Lite.
A solid lineup of competitors.
Definitely. And the results, well, they look pretty promising for Unicorn.
How so?
Across most scenarios, Unicorn generally came out on top. It showed, significant improvements in those key metrics, queue length, speed, delay.
Especially in the tougher networks.
Exactly. Those complex, heterogeneous ones, like a big 5x5 grid simulation, that's where it really seemed to shine compared to the others. Places where generalizing and collaborating effectively is crucial.
And that ability to generalize, that seemed like a key finding too, right?
Absolutely. The results suggest a single Unicorn model, trained on diverse networks, could perform well even on networks that hadn't explicitly trained on.
Which is huge for real-world deployment. You don't want to retrain from scratch for every single city block.
No kidding. Imagine the cost and effort. A universal model that adapts quickly. That's a big step towards making these systems practical and scalable.
They also did that thing, the ablation study, where they take parts away.
Yes, very important. They systematically removed bits of Unicorn, took out the UTR or the ISR or the contrastive learning part or the collaboration piece to see what happened, and it confirmed that, pretty much all those components were important. Removing any one of them tended to hurt performance.
So the whole design hangs together. Each piece is pulling its weight.
It seems so. It validates their design choices, showing that the UTR, the ISR, the contrastive learning, the neighbor info, they all contribute meaningfully. The ISR capturing those specific details seem particularly vital.
Okay, so stepping back and putting it all in perspective, Unicorn looks like a really, innovative approach to this persistent traffic problem.
Yeah, right.
By using that unified movement representation, learning both general and specific patterns, and building in that collaboration, it feels like a definite advance for intelligent transportation systems.
Yeah, it suggests a pathway towards signals that are much more dynamic and sophisticated in how they adapt, potentially leading to, smoother commutes, less wasted time.
And if we think historically, we went from fixed timers to basic adaptive systems.
Right, SCOOT, SCATS, things like that. Then came AI, machine learning, often centralized at first.
Then the shift to decentralized multi-agent RL to handle the scale of cities.
But those early MRL methods often struggled with generalizing, with that heterogeneity problem we keep mentioning.
So Unicorn is kind of a response to those limitations. It draws on newer ideas from transfer learning, representation learning.
Absolutely. It's building on progress in other AI areas. You could almost draw a parallel, maybe, to how early NLP models struggled with language diversity before things like word embeddings and transformers came along.
Like the UTR using that transformer-like architecture, a more universal way to represent the language of traffic.
Exactly. It's applying those powerful representation learning ideas to this domain.
Okay, cool. That sets the stage really nicely. Now it's time for our Novel Notions segment. This is where we brainstorm a bit, think about where this research could go next.
All right, speculative hats on.
Given what Unicorn can do, what's an exciting potential next step?
Well, one thing that comes to mind is expanding the types of data it uses. Right now, it's mostly traffic flow, signal states, standard sensor data, basically.
Okay.
But what if you could feed it richer, real-time info? Maybe video feeds processed to detect accidents or sudden lane closures, or GPS data from connected cars for super granular traffic patterns.
Ooh, interesting. So how would Unicorn handle that?
Well, you'd need to figure out how the UTR and ISR modules could process and fuse that multimodal data. Could they learn to use, say, a video alert about an accident to make proactive signal changes before gridlock sets in?
That connects to their mention of future work on incident adaptation, right? Making it more resilient.
Exactly. Taking it a step further with richer real-time inputs.
That's a really neat idea. My thought was maybe pushing the generalization aspect even further.
How so?
They showed good results with joint training on diverse data sets. But could we apply meta-learning? Train a meta-unicorn that doesn't just learn how to control traffic, but learns how to learn the specifics of a new network really fast.
Learn to adapt quickly with minimal fine-tuning.
Yeah. Imagine deploying it in a brand new city it's never seen. Instead of massive retraining, a meta-learned unicorn could maybe pick up the local patterns much faster, like a meta-UTR and meta-ISR that are optimized for rapid adaptation.
That's also a really compelling direction, improving not just the performance, but the speed of deployment and adaptation in totally novel environments.
Game changer potential, maybe?
Both ideas, richer data integration and meta-learning for faster adaptation, seem like really fruitful avenues building on this work. It shows the potential here to spark more innovation.
Definitely. And just our usual reminder here, Novel Notions is just us thinking aloud purely for entertainment and sparking ideas. The actual research might go in totally different directions.
Of course, speculation only.
For the real deep dive into Unicorn's technical bits, the architecture, all those experiments, definitely check out the paper. We'll have a link in the show notes or description.
Absolutely worth a read if you're interested in the details. It's a solid piece of work tackling a really complex, important problem.
A great example of ML being applied to, tangible, everyday challenges.
Couldn't agree more.
All right, that wraps up our deep dive into Unicorn. Thanks so much for joining us on Talk Tensors.
My pleasure.
We'll be back next time to explore more cutting-edge machine learning research with you.